fairly expensive book, at least if you purchase the hardcover. There is a soft cover which is half the price or something like that. There are some earlier editions out, but well, then it's your responsibility to make sure that the content in the book corresponds to the content in my lectures. Okay? So, the first lecture will be on an introduction to systems and software engineering. So I'm not sure if you ever considered what is a system here. What is the term system really mean? Well, the definition here on in the presentation here, it says that a regularly interacting or independent group of items forming a unified whole. Some examples. Well, we're dealing with software systems here, and it's obvious that in a software system we have regularly interacting and independent group of items. We can have different objects, we can have different subroutines, etc. So that a software system, well, the systems we're dealing with in this class, they are pretty special in some aspects. And what's even more interesting is that we can combine these software systems into systems of several software systems. We see that today when we constantly access other systems using, for instance, your mobile phones or your computers, like a web browser that connects to a web server. That is, in fact, two systems that interact. Recently, one other class of systems have really exploded. Today, we see a huge number of what's called cyber-physical systems. And these systems are very special because here we combine software with hardware. So software that controls hardware, for instance, or software that has some effect on hardware, or vice versa. And in a situation like that, when we control hardware, you can imagine, for instance, a situation which is a reality today where we have software that controls the brakes in your cars. Software moves now into a domain where the consequence of a failure is no longer just an upset user banging the keyboard or something. It can actually be a car crashing. So understanding these systems are becoming more and more important, more and more difficult and challenging. And what we will do in this class is to give you a first shallow introduction, understanding of things that you can do and must do in order to be able to develop systems like this. So what we are looking for here is that someone must take control. These systems are complex, these systems are impossible to grasp for a single individual. We must have someone that takes control. And someone must take control over the system. What do we mean by that? Well, in order to develop a system, we must define what is the system, what is in the system, and what is not in the system. That's the first step. One of the questions we will answer in this class is how to do that. Second, we must understand the parts. Remember, the system was a set of interacting items. So we must take control over these parts, defining which parts do we have. What are the responsibilities for the different parts in our system? And of course, it was more to it than just the parts. The parts were interacting. So in the same way that we describe or define the responsibilities of the parts, we must also define the interactions. How may these items interact? On top of all this, as I said before, no single individual is able intellectually to grasp systems of these sizes. So this is and will always be a group effort. So someone must take control over the people that develop, that maintain these systems. So what we're aiming for here is that we should engineer systems. We should not develop them. And the reason why we make this distinction is, well, I want to come back to this braking system controlled by software. We would like to develop software in the same way that we engineer bridges. We want to engineer software because we want the results to be predictable. We don't want any mishaps where the braking system fail just because. So, some characteristics and some problems of system and software design. The characteristics, well, they are complex systems. I mentioned this to you before. We're talking about many different parts. We cannot understand them all. We cannot understand each and every interaction, at least not individually. We must do this as a group activity. And software and systems engineering always have this kind of first time label attached to it. There's always some new piece of technology. There is always a new individual in the development team. There is always a new programming language or something like that. So it's rarely the case that we repeat exactly the same effort with the same customers, with the same customer goals. Because if we do that, we can just take a system that we have and copy the software, purchase the same hardware pieces, and put it together at the customer site. But that's hardly the case. So, the problems then is most often found in aligning the work of the individuals. It's a group activity, yes, but each and every individual must work in the same direction, because if people work in different directions, well, it will not be possible to control the effort. So the results are most likely not predictable, and that was what we were aiming for. On the other hand, we don't want this group activity to be a group activity in the sense that everyone is working on everything together, because that is not efficient. So in order to make things efficient, well, we want these guys here to work individually but aligned with the same goal, with the same understanding of the system, so that we at the end of the day end up with something that is coherent, where the different pieces conform to the overall plan. So decomposition is key here. When we deal with complex systems, well, and you may pick any system, really. It doesn't matter if it's a biological or, well, any type of artificial system or an organization. They are all, well, possible to decompose, because most of these systems, or all of these systems, consists of something that is dividable into parts. So we can decompose them into subsystems. And these subsystems can be further decomposed and further decomposed. And we can go on until we have something that is fairly manageable. And that is the key to solving these complex problems. They were impossible for an individual to grasp, but what we have here is an opportunity that we might or should exploit. We can decompose and we can say, okay, if you develop this subsystem and you develop that subsystem and we define the interactions, you guys may go to your own offices, develop the system separately, and then come back. Because if you're both conforming to the rules of decomposition, the items should be possible to put back together into a larger whole. Okay? So problem solving then is all about finding the best pieces and join them together. Or, well, I would say no, because just defining the interaction points here is not enough. There is more to it, because it is not possible to define and identify all interactions up front before we do the actual work on it. So sometimes pieces in the system will not fit. They will not work together. And this means that we have to do something more than just identifying the pieces, develop the pieces, put them back together. And that is, we must validate that the system we have put together is working. So what you see here is more or less the 4 engineering activities that we go through in all projects. Finding the best pieces, well, that's about first understanding the system that we're about to build. Then defining the decomposed or the decomposition, the pieces in the decomposition. Implementing or developing or purchasing these pieces, put them back together. And the final step then is the validation, to make sure that the pieces fit. So, engineering software. People like to make a comparison between software development and their early days of aviation. And for large systems, this has changed. So we're not building the complete system, the car, just to find out that the braking system fails. We do it differently. But developing software, since it's a system, well, the items that are also systems, they meet the same problems there as for the larger system. They are complex. They must conform to some environment, other components. They are easy to change, and they are not easy to see because they are software. So besides having this square peg and put it into a round hole thingy, we also have this financial aspect of things. We must do this under, well, some budget constraints. We have constrained resources in terms of people, money, etc., etc. So the course goals, how to develop high-quality software systems. Well, that's a big bite for a first class in software technology, software engineering. So the goal here is that you should understand how to do this on a high level. Understanding and grasping all the detailed techniques and technologies and so on, that's, well, the goal for coming courses in your study program. But to make software visible, for instance, we need to work with models. So how to create, refine, and maintain adequate models describing your software, how to implement and verify them, and also to manage the people involved in the development. So it's not that easy as you may have read in some magazines, that if you just let the programmers free and develop in an agile way, everything will go smoothly. It's much more challenging than this. You know, you must crawl, learn how to crawl, learn how to walk before you can run. And this is about learning how to crawl. So the course goals in more detail is actually about you guys understanding a structure that you can follow when you work as a group in a project team or as an individual. Before you start working, you need a plan. You need to plan your work. And at the end, you should reflect. Reflect on the result, reflect on your plan, reflect on the resources you have used. Because in real projects, this is very important, because you will be a resource. You will cost money. And planning and reflection will train you to better understand, well, how productive you are and how productive your team is in a project. And that's very important, because you will, from time to time, have to answer questions like, when can you deliver? Have you defined all the user stories? Have you found them in your discussions with the customer? Well, if you want to answer these questions, you must have thought about them before. And the activities you should plan is, and these are, well, generic terminology, understanding the problem, defining the requirements for what you should do. Further understand in detail what you should do and come up with a design of your software and your system. Implement this design and then test it. That's the validation part, to make sure that the pieces you implemented fit together. And it doesn't matter what name your process has. You will always go through these steps. And these steps will have different names, but the purpose is similar, at least in nature. So these are the activities. However, well, we have something more to it, and that's the people performing the activities. And planning your own activities, planning your team activities, planning the entire project is also extremely challenging. So we will start with a brief, scratching the surface of planning, so that you should get a better understanding for how to do this. So planning, well, understanding a process means, well, to focus on three types of entities. The guys involved in the project, the stick men here, stick women too, they perform in different roles. So sometimes I'm the project manager, sometimes I'm the developer, someone else could be tester, requirements analyst, different roles. More. These roles, they perform activities. And activities produces work products like documents code, etc., test cases. And they also consume work products. A software designer designed a system based on the work product requirement specification, to make it a simple example. So any software process can be defined using these three concepts. And this is something that we will spend a lot of time on in this class. So the 1940s, problem solving with programming. This is coming from craft to engineering. Well, this is a nice little picture on the right-hand side here, one of the first computers ever. You can see that, well, implementation was fairly complex. It was patch cables that you had to move around to program your software. So at that time, the capacity of the implementation technology set the limits of what you could actually do with your software. So at this time, often these, well, guys here, a programmer, analyst, worked with testing, they did it all. So there was not really a process here in the way that we had tens or hundreds of people working on the same project. It was more like a small group that could use more of a straightforward mathematical approach to solve a problem and implement it. However, the increased complexity, and since you guys are much younger than me, you can just make a comparison with the gaming industry. Games impose new requirements on faster, better hardware. And as better hardware is made available, that will impose new requirements on better, well, more advanced games. So there is this duality. And this, of course, increases the complexity of both the hardware and the software. So more complex problems, of course, requires more complex solutions. And this continued for some years, but in the mid-1960s, the Department of Defense in the United States, they, at the time, they were the biggest customer purchasing software. They well, recognized a situation that was well, it couldn't continue like this. And they actually coined the term here, the software crisis. And the software crisis, well, their projects were always over budget. They were always too late. They were always of low quality. At least, well, the software that was delivered was not in line with their expectations. And adding to this, they were also difficult to manage, to maintain, and so on. So I would say that if you purchase software that was more expensive than, well, you expected, you didn't get it, and when you get it, it's not in line with your expectations, and it's difficult to well, install, difficult to update, etc., you would not continue buying software from that software house. So the Department of Defense, they said, okay, we must do something about it. We must go from crafting to engineering. Or, well, craft. We know that skill in doing or making something, as in the arts, proficiency. Okay, system and software engineering is predominantly an intellectual activity. So we use our brains here. And there is no doubt that there are excellent individuals that are extremely skilled in developing high-quality software. However, at some point, it must become a group activity. And since it's an intellectual activity, the result depends on the individual's skill. And it means that, well, if we have a group, the resulting system is affected not by a single individual, it's affected by all people involved and their skills. So, second, we cannot have, or we can have, but it will take lots of time, we can have the traditional apprenticeship where we have programmers learn from other programmers for a couple of years, but it's still dependent on the individual skills. So we need something to control, take control over the individuals, to guarantee that the output of our projects are not that dependent on the individuals involved. It should be, at least from a company perspective, different. It should be same results or similar results independently of the members of your development teams. So, we would like to go from craftsmanship to engineering. Because engineering is more predictable, much more predictable. It's repeatable and transferable. So we can transfer the same work descriptions from one problem domain to another. And we will still get results similar in nature. So the difference between craft and engineering is that the engineer is a little bit more cautious. And the engineer is much more explicit in terms of writing down that we do this, we do that. If you look at the very skilled individuals, the good programmers, the good craftsmen that we have in our business, they are doing this. They are doing this all the time. They are probably doing it better than an engineer, the average engineer, but they do it in here. They're not very, it's difficult for them to involve other individuals in this activity. So that's why we have to somehow externalize these activities to make them available to everybody involved in the project. So, what are we doing? Well, we are solving problems. And this is a Hungarian mathematician, Polya, and he has this problem-solving process. And I guess that all of you apply this process when you solve problems. And this is exactly what we're doing as software system developers. We solve problems. And we solve the problems with software. So our solutions will be software or systems with software or plain software systems. And we use software-specific methods to collect requirements, to do the analysis and design, to do the implementation and the testing, validation, verification. So, it is necessary for us to go from craft to engineering. Not excluding the brilliant individuals out there, they are doing a great effort, but for most of us, we need this to be able to deliver on time, deliver on budget, deliver in line with expectations from users, and deliver something that someone can maintain easily, someone can upgrade, update, etc. So we want something that is predictable, we want something that is repeatable, and something that is transferable. And we achieve that by applying, what is say, sciences of physics and mathematics. What is that? Well, sorry. Can be a technical problem here. Yes? It wasn't. Anonymous calls. Sorry. We apply the sciences of physics and mathematics to find suitable solutions. That is that we can actually develop techniques, develop methods where we have some sort of guarantees that what we're specifying, what we're modeling is correct. At least we can have some kind of, we can believe, we can have some probability that a model is correct. Another thing that is very important is that if there are alternatives, and most often there are alternatives, well, then we compare alternatives and pick the one that fits our solution or problem domain the best. Engineering should be predictive. That is that, well, this is to avoid this, develop the entire system before and then test it. What we do here is that we attempt to predict how well the design of our system meets the requirements before we start to produce it. So we want to avoid this, build the entire car before we test the brakes. We actually start with modeling the brakes. We test the behavior of the modeling, the software, and then we integrate the software with the hardware, and then we test the integration of that before we put it into the car. So, software technology, which is the focus of this class, is the profession concerned with specifying, designing, that's the problem side of it, and going from a problem to a solution, developing and maintain these applications by applying technologies, not just from the computer science domain, but also from, well, other domains like project management. And as I said before, there are always projects, your hobby projects, that don't need all the bells and whistles that we will talk about in this course. But if we talk about industrial software, for a cyber-physical system, for instance, well, a company will not develop software for a car without providing guarantees that it will work. And the techniques we will look at here, or will study in software engineering, is about providing the evidence the company needs. So it's a little bit of this programming in the small versus programming in the large, where we will start to look at the programming in the large aspect of software development. Because, believe it or not, software development projects fail from time to time. And failures could be extremely costly. These are two, well, they have we're a couple of years back, but it often takes a couple of years before these failures surface because of, well, companies don't want to, they don't put this in their ads, so to speak. But there was one airport that couldn't open because the baggage handling system didn't work. You know, you can't run an airport without a working baggage handling system. So they couldn't open. And that costs, well, hundreds of millions of dollars. There was another example, which was an ambulance dispatcher system in the UK. And, well, this was a system failure because it was not necessarily just in software the problem where it was actually a problem with communication with the ambulances. So they could, or they found some cases where ambulances were actually not sent to the people calling. So there were some casualties actually due to this failure. So it's not just the angry, upset user. Sometimes a failure is much worse, sometimes even fatal. So what is the root cause? So what are the root causes here? Well, complex systems involving people, not just people developing the system, people, the customers, the purchaser of the system, management in your own company. Well, it's about communication. Lack of communication, communication of low quality, well, making the people involved that has a stake in your project communicating in the right way. That's the key. That's the key to a successful development project. And this is a cartoon that maybe some of you have seen it. It's just to illustrate the communication in a development project. And we start with finding out the problem. And we look at how the customer described the system they wanted us to develop. And this is our understanding, or this is their presentation of the problem. This is a swing. It's as you can see, a slightly improved swing with possibility to put 3 people on it, I guess. Or, well, this is how the manager understood it. Okay, as you can see, it's, well, similar, but definitely not the same. So we continue and we start coming up with a solution to this problem. And now you can see that, okay, communication has already made it extremely difficult to provide something that the customer was initially asking for. So what the architect then ends up with is something like this. It's a nice little compromise where there is always a tendency to meet your own management's expectations than your customers. So continuing from this, well, then we have the developers. And the developers should transform the nice structures from the architects into a code representation that can be compiled and executed. And they get something like this. Yeah, it's a swing, but it's maybe not very useful, at least not for what the users initially described. However, well, we have the marketing department, and they, of course, they market the product like this. And it goes on like this. It goes on and on and on and on, and it's all about communication. So documentation, this asynchronous way of communication where you actually put information down on paper or store it electronically, well, we all know how fun it is to document. So maybe there are some, well, faint traces of what we actually implemented. However, we deliver something. And we deliver something to our customers, and they get this. But then they have to pay. And what do they pay for? This. A roller coaster with, well, the ultimate entertainment for your own garden, of course. But then we have received the payment from our customers. So as most other organizations, we are not very interested in supporting the system post-deployment because it's expensive and it's more fun to go on with a new project because that's where we earn most money. You know, the big software houses that sell, well, for instance, office packages, etc. You don't have to pay for the updates, do you? So you pay for the package initially, but then the updates are for free, at least, well, for some time. So this is costly, it's not very fun, it's more fun to continue. So what did they really need? Well, they wanted this, but they described it like that. And this is another problem that we face as in software development. The customers, they don't understand how they should express themselves in a way that we can understand them. And this is very difficult. I can give you a small assignment, something that you should think of during the break that we will have in a couple of minutes. You should be able to instruct, to tell someone how to ride a bicycle. Can you describe that? That type of knowledge is extremely difficult to express or to document, to communicate to someone else. Get on the bike and start pedaling? That's more to it. Okay. So the difficulties that we meet when we deal with software is first the inherent complexity. We're not talking about the small software systems where we have lines of code in the hundreds or the low thousands. It's much more complex than that. So the component interactions will make the possible states that a system can take on to grow exponentially. So adding just a single line of code may increase the complexity by an order of magnitude. So this is something that we must deal with when we develop our software. Second, changeability. Our software is often a representation of something, a process or some artifact from the real world. And we all know that the real world is changing. It can be anything from rules or law, well, from the government to new technology that arrives on the market. And this change, there's a constant pressure that, well, software is so easy. Of course, you should meet these changes in software. Hardware, for instance, is much more expensive. It has a longer turnaround time from idea to finished product. But software, it's just, well, write a couple of lines of code and you got it. The problem, well, a few lines of code could make the complexity explode. Conformity. A system must interface with existing, well, surrounding systems. Well, it's not just a, well, cell phone here that, well, it interacts with several other different systems. And of course, this phone must conform. If you want to use it to make a phone call, it must conform to the protocols, to the physical restrictions of the cellular phone network in your area. Then we have the data communication on top of that, and sometimes we use or most often use a Wi-Fi indoors, and then it must conform to that system. And then you have your applications, your apps in your phone that conforms to the rules imposed by a vendor like Apple, or rules imposed by some provider of information. So when we develop a system, we must also understand the surrounding systems, at least to some degree, so that we can conform. And that's challenging. Finally, software is invisible. We're not building bridges here. We're not constructing houses. Bridges and houses, we can see if something is going wrong. The problem with software is that we can work for a long time before we see that we did something wrong early on. So the challenge here is to be able to visualize representations of software early in development so that we can see if we make mistakes. Okay? So that's about it for the first part, and now we take a 15-minute break. Okay? So, welcome back to the second part. We'll continue with the introduction lecture to systems and software engineering. So before the break, we spent some time on, well, trying to frame what a system was, some of the inherent challenges in software and systems engineering, and well, it was not just the system or software that we're supposed to develop here. It's also us that we're part of the problem. People involved in development, people involved in the projects as customers or any other stakeholder. They are also difficult to manage, and to take control over the system and the people involved. That's key if we want to succeed with our development projects. So the four essential difficulties here that are listed on this slide. Well, complexity. How do we deal with complexity? How do we humans deal with complexity? Well, in principle, there are two strategies that we employ them every day, constantly, all the time. They are so natural that we don't even think of it. So one is abstraction. Abstraction is concerned with reducing the amount of information we need to process in order to understand, to talk about something. So we simplify the world. We abstract the world. And this simplification is based on the current context. Current context? Yes. When we develop our software, it has a context. So if we're developing a tax system for the tax authorities, the abstraction of a person, an individual, that's different compared to a system, the abstraction used in a system where a person is just a member of a soccer club, for instance. We use different properties to describe a person for the tax authorities compared to membership in a club. Some of the properties are similar, but some are different. And we don't use all properties in any of these two. We don't have shoe size. We don't have hair color, length, etc. in any of these systems. However, in some system it may be useful in that context. So the simplifications, the data abstractions, the instruction abstractions we use in coding, for instance, they are excellent examples of how we use abstraction. You know, the little plus sign character where you can add two variables? Well, that is an abstraction of a language that the processor inside the machine understands. It's actually a series of instructions required to perform an addition. Okay? So we use that simplification. Otherwise, we had to deal with all the details all the time, and that takes our focus away from the core problem, from solving the core problem. Okay, abstraction is one way of reducing complexity. The other one is decomposition, and you've seen examples of that already. But creating abstractions is one way to decomposing a problem. So we simplify into abstractions that we're used to decompose the system. And now we can focus on a part of the system, understand that, then focus on another part and understand that, and the interactions in between. That reduces the amount of information we need to process. Because, believe it or not, I know it's difficult to accept, but we are like, to some extent, well, there are limits to our intellectual capacity. We're not able to process that much information at the same time. So we must switch focuses from one focus to the other. These context switches that people feel are annoying when disturbed are actually something that we use to deal with complexity. So we throw some information out when we focus on this, and then when we focus on that, we throw some information out and take in new information. Just to get around the limitations we have. So we decompose subproblems and further decompose them into subproblems. And this divide and conquer approach is one of the most widely used problem-solving approaches. Something we use all the time, every day. We just don't think about it. Just getting to the university, if you consider that a problem, you can divide it into wake up, that's a problem for some. Get out of bed, make breakfast, get on the bus on time. That's a problem, especially in Sweden when we have like fresh snow in the morning. So you divide this problem of getting to the university up into eatable chunks that you can chew one by one. Because if you focus on the bus while preparing breakfast, well, you may, burn your eggs or something. So next, besides the complexity, we had this changeability. And changeability is something that is, it's getting faster and faster and faster. If you're not moving at the speed of the marketplace, you're already dead. A couple of years ago, 10 years almost, there was a cell phone brand, Finnish brand called Nokia. They had like 45, almost 50% of the market. Then there was this player, Apple, who started to sell a phone that was not in par with any of the existing phones in terms of the hardware specification, performance, etc., etc. But it was different. And I know that the managers in the existing players in that ecosystem, they looked at this phone and said, no, we continue. We're like 45% of the market. We make the decisions. We make the calls here. And we know what happened. So you must go with the flow. You must, well, take the lead if you want to stay on a market. And this is true for software, of course. If you want to be, well, continue your success stories, you must be at the front. And how do you deal with the change? How do you deal with the change? Well, you have goals that constantly change. Someone is constantly pushing the limits. Well, in order to work with systems over there, your way of developing these systems must, of course, well, be prepared for change. So the processes, the activities you perform must always take change into account. When you code your method in whatever language, you should always ask the question, if this will change, what will it take to change it? When you write up a requirement in whatever format, what will be the consequence if this requirement changes? Or if some other requirement is changed that this requirement is affected by? So always have this change. In front of you when you work with processes and models. What else? Well, things go wrong. We saw some examples, and there's this famous Murphy's Law. If it can go wrong, it will. Yesterday I had a lecture in this room, and believe it or not, something could go wrong, and it went wrong. Nothing worked. I had to close the lecture after 5 minutes. We're much better off today. Knock on wood. So what you should do there then is you should always be prepared for the unexpected. And another word for that, the unexpected, is risk. So when we talk about student assignments that you do together with your best friend who never shows up in the lab sessions, that is a risk. How do you manage that? Well, one mitigation plan can be, okay, find another friend in the class to work with. Or give the guy a ring and say, hey, where are you? But you should be prepared. You shouldn't sit idle during the lab session for 45 minutes waiting for your friend. And this is part of the game, part of the planning, part of the actual engineering of your systems. Because there are some risks related to the project, and there are some risks related to the product. We all know that technology plays a big role in our projects. So we we invest money in a database management system, or we purchase some consultancy service or whatever. But we do that under the assumption that our evaluation, you remember the engineering practices, our evaluation of the management system or the consultancy service, we're actually up to it. But if What if they don't deliver? What if this database management system, well, fails when it comes to, well, say that we have too many hundreds of thousands of simultaneous transactions. What if? What should we do? That's risk management, because this is actually true. If something can go wrong, it will. Not every time, but sometime. So the invisibility, how do we manage that? Well, we talked about a simple example before the break. Did you think about that? How to tell someone how to ride a bicycle? Tacit knowledge. Knowledge that is difficult to explain in words. That's a very good example of invisibility. How can you do this? And you should know that it's not just systems where you need to teach someone how to ride a bicycle where you will find tacit knowledge. It's everywhere. You know, first day in school, you could probably, at least I can, repeat most of the day, my first day at the university. And that's 25 years something back. But I still remember how nervous I was when I was entering the lecture room among the 150 other students. I remember who was talking, I remember what we did after that, so on. Do I remember the 35th day at the university? No. And this is like something that reoccurs in whatever we do. We tend to forget what we do. Processes are automated, and if you go out and ask some administrator, for instance, working for the tax authority, what do you do during your work day? Tell me, because we're going to build a system that replaces you. No, but we're going to build a system that helps you. So how do you do this thing or that thing? How do you do that? Be prepared that this administrator, there is lots of tacit knowledge that they forget to tell you, not on purpose, just because that's how humans are. And of course, this goes on and on. So when we sit with our fellow designers, designing the system, you come up with a brilliant idea. And you say, I have a brilliant idea, and here's the idea. But in order to, well, talk your friends into, well, accepting this design, well, you have to communicate. You have to provide information that makes, well, the design, the consequences of the design visible to them. And this goes on and on. You need to visualize your intentions. You need to explain what you want to achieve. That's why we ask you to comment your source code. Because source code, that's abstractions. And what did we do when we abstracted? Well, we throw out information. So now let's throw back some explanation so that we may communicate better. So the models we create, they support communication. That's why they are so important. So the guys down here in the corner, they communicate. And if you want to communicate, you can communicate in Swedish. Då låter det så här. Och då är det inte säkert att alla förstår. And understanding is important. It's extremely important if you want to align the group of developers to work in the same direction, sharing a goal, under the same constraints in terms of quality, etc. Well, you need a language that they can share so that they can communicate the design, the brilliant design that you came up with. So how can you communicate that in an efficient way? Swedish, English, something else. And the models, that's actually a language that we use as software engineers to communicate, to make our communication more efficient. The products we develop, they are systems. The process we use, that's also a system. Remember, we could divide a process up into process roles, into activities, and into work products. A decomposition. We can actually see that these are also abstractions because we have a process role and we have many different roles that can be applied on, well, individuals. Here are some examples of process activities. Things that we go through during a software development project. Requirements engineering, design, testing, configuration management, implementation, product management, quality management, product management. Depending on the organization you will work in, this list will be different, but will differ. But these are like core activities, and in the same way that we communicate products using models, we can communicate process activities using models. The first challenge here is to look at the interactions of these parts that we have in our development system here. So we do that using different process models. So we can organize these activities differently, and well, there are, well, I listed some famous processes. The waterfall process from the 1970s, the spiral model by Barry Beam from the 80s, the unified process from the 1990s, and then the agile movement during the early 2000s. And I can say one thing: something else will come. Because in the 70s, the waterfall was it. That was the answer. Use the waterfall model and there will be no problems around. The spiral model, do it that way and there will be no problems. But things change. So what's hot and what's not, it changes over time. But
is the agile process the most used today?
That's not, so the question was if the agile style of processes are the most widely used today. That's not an easy question to answer. I would say that if you ask companies, well, the reason why it's not easy to answer is that if you ask companies if they use agile development, you get more and more often you get the answer yes. Because if you want to sell something to a customer, the customers, they heard so much about agile development, and agile development is good, and of course they want to purchase the software from a company that says that, okay, they follow an agile process to develop software. However, there's always a catch. However, if you go in and study the companies in depth, in more detail, it's like shades of gray. So you have some guys that are yes, definitely. Some guys that are yes, and some that are yes, and some that are no. But they're all claiming to employ an agile process. But I would say that this is something that has grown dramatically in the last 15 years. So there is definitely something good to it. But if you go out and look at, well, some of the bigger enterprises, what you will find is that, okay, they do agile, well, that they have shoehorned into their, enterprise processes just to make things work together. You know, like a large company, a Swedish company like IKEA, they have hundreds of systems. that must work together. So they can do agile at all levels. They can do agile down here, or here, or here. But they must have conformance between all their systems. So they have processes at different levels, and they can't be agile everywhere, all over the place. So I would say it's impossible to answer that question. But if you go into a small company, a startup, developing for the web or something, I would say that these are probably on the end of the scale where it's yes, no, not too much hesitation. Okay? Hope that answered your question, or maybe I just confused you more. So, organizing work. This is the process from the 1970s. The waterfall model. And this is, as you see from the original paper, a scan. And this is my favorite process, actually. As a student, this was the process I used without knowing it. So there are two essential steps, regardless of size or complexity. First, you analyze, then you code. That's it. Yes, at a very abstract level, this is what you do. You understand and you implement. But you must make sure that your understanding is correct and that your implementation is correct. And this is similar to what you see in Agile. Agile claim to do less. Well, as we will see during the next lecture, it's actually not doing less, it's being less prescriptive. You should do this like this. You still do it, but the process doesn't tell you how to do it. So as with any abstractions, you can go and have a look, and you might find a further decomposition into the parts of analysis and into the parts of coding, and there you will find a step where you actually make sure that you have the right requirements, and a coding step that involves a design, an implementation, unit testing, integration testing, system testing, etc., etc. So, dividing the work up here is not a straightforward operation. You need to, well, think carefully to get it right. Excuse me. The first, well, a force here is like something you use to guide your decomposition of work, an organization of work, to divide the work up into chewable pieces, more or less. So one of the forces you may use is something called milestones. That's similar to what I used as an example before. You wake up, you get out of bed, you make breakfast, you get dressed, so you have like a sequence of activities. So hopefully you get dressed before you get on the bus and so on. So you make sure that you achieve certain sub-goals before you continue. In the software development process, a milestone approach is often document-driven. It has the perspective of a manager who's interested in controlling progress in a project. So the goal here is like 2 weeks from now, this artifact should be ready and signed off. It should be like ready, inspected, approved, signed off. Okay. But you can also use releases. You can say that, okay, 2 months from now, we should have a demonstrator of the system, the principal architecture of the system up and running. Then another 2 months ahead, there should be like a feature complete system app that we can deploy. However, the perspective here is more Who's doing what and when is it done? It's not really the product in focus, it's the process itself in focus, that you go through the steps here. So it has more, it's more directed inwards, towards the development organization. But at the end of the day, that's not what put bread on our tables, that's the customer that does that. And they are interested in the product and the value we deliver to them. So instead, we can shift focus slightly and see if we can't shorten the time in between our releases, because a release is a very useful interaction point with customers. Please have a look at our release. Is it something that you want or not? So with the swing example, for instance, if the architect could have visualized the swing they designed, well, the customers would probably have said, no, this is not what we wanted. So if we can shorten the time in between these interactions with customers, well, we will have smaller steps. We will actually have a sequence of smaller projects. It will not be one huge project. It will be a sequence of smaller projects with feedback that we can use to improve. And we all know that smaller time frames, they are much easier to plan. If I ask you guys to plan for the entire course, what you should do each and every day, every hour, it will be quite of a challenge. But if I ask you to come up with a plan for the coming week, it will be chewable. Challenging, but still possible to achieve. If I ask you to come up with a plan for tomorrow, no problem. So this is an example of, well, shortening the time frame. Question?
Is this part of the waterfall model?
I would say that this is, if you look at the waterfall model had the intention was, okay, you have a number of steps that you have to go through. And well, some people say that iterations are not existing in the waterfall model. That's not true. Of course, you go back and do it like that. But the waterfall model is more milestone driven. So the focus there is not iterations and increments to have increments on the product. It's more about, well, delivering specific documents. So it's not incremental, but it can be iterative. However, what you will see, these mini projects that you get when you divide, well, your work up into iterations, they're actually small mini waterfalls because they describe the activities that you go through. So iterative versus incremental, and this is an example that I borrowed from a company presentation. An incremental plan. So we have a goal at the end, and that's to complete this drawing. And as a painter, we start with we'll complete the facial part of the painting, and then we continue with a mid part here, and at the end of the day, we have completed this part. So a very simple analogy to software and system and software development is that, okay, this is the server side. This is the mid delivery 2 is the server plus business intelligence. So the logic on the server side. And then delivery 3 is the server, the back end, server business intelligence, and the client side. So we'll prepare each and every of these incrementally. There are some difficulties here. One of them is that, okay, we don't face the complete integration until, well, the end of the project. So the client is not ready until the end of the project. And that was not good because, well, sometimes, well, we make mistakes, and the only way to discover these mistakes is to actually go all the way to implementation and verification. And one of the mistakes we may make is that there may be an integration problem from the client to the backend through the business intelligence. And one way to get around that is to use an iterative plan. An iterative plan is well, it can be, you can combine the two here, of course, but you can what you see here is like, okay, here is like just like sketchy, not very detailed, but it's still like, it's still the painting. You can see that this will be the final product, okay? And you can show this to the customer, and you can ask the customer, hey, what do you think? I'm drawing this lady here. What do you think? Do you like it? And at this stage, the customer may say, no, I want a hat. The lady must have a hat. Okay, so then you can go back to the drawing table and you can, well, put a hat on there. But, well, in that interaction, the communication with the customer, what you get is actually feedback. Okay, so you can go on and you can improve the picture. It's still blurry, but you can see, well, there are colors, etc., etc. So now you can go back to the customer, and the customer can say, hey, well, this is, looks good. And then you can finish the product. So, different perspectives. And what you see in today's process models is actually, well, we combine this. We cannot focus on the entire system all the time, so we pick out the most critical parts, and we iterate on that until that is stable, and then we can pick some other part. So we combine incremental and iterative. So why do you do this? Why do you prefer to provide something, communicate something to the customer that well, captures the essence of the final system? Well, it's risk management. It's risk management. Think of the hat example, but turn it around. Say that you put a hat on the lady from the beginning without asking the customers. That was your interpretation of the customer requirements. The lady should have a hat. You show it to the customer. Well, if it's here, you discover that mistake, it's okay. There is some work needed if you want to restore the picture to a lady without a hat. However, if it was here, it would be more. When I use this example, there is always some smart guys say that, hey, it's paint, so you just paint over. Yeah, it's true, but think of it in a system context. You need to change, you need to modify code, you need to change your design, all this and that. It's risky business. So risk management is to well, avoid problems. So early in the projects, you focus on risk to remove risks from your project, and well, having the big picture, having the system architecture, the big picture of the system set and accepted by the customer early in the project, that is reducing the risk dramatically. You know that you're at least in the right country in terms of your solution. And when you have reduced the risk, then you can start to add value. You know, change your color schemes, include avatars and stuff like that. Adding an avatar feature, it's not a big deal compared to having the messaging system up and running. Risk reduction before value addition. Because it doesn't matter how much value you have if the core of the application is not there, then the value is worth nothing. So as an engineer, Always decision based on facts, not on guessing. And this is something that you go on with throughout your project, because selections you make, design decisions, implementation decisions, they create new risks that must be mitigated. As you will see here, there are this is just a very short list of risks. And it's not just staff. There's many different types of risks you must understand. You must put them on the table. You must discuss them. You must find mitigations for them, to remove them or to get them under control. So, today's takeaways: system and software. A very interesting area, because solving problems, it's fun. You get feedback from the people you solve problems for. That is, well, a wonderful experience. It's also a team effort, and that makes it, well, even more fun. And also a pain from time to time. But what's important here is someone must take control. You must frame your system, identify the boundaries, what's in and not, which parts are the system made up of, how do the parts interact, and how should we organize the people that are responsible for the development of the system. And what's important here is that we have engineering principles that we apply. And in the software development project, the process here includes roles, it includes activities, and it defines different work products. And these guarantee that the engineering principles are applied. Or at least, maybe not guarantees, because it's people involved, so we can do whatever at the end of the day. But the system, the process, should guarantee that even though an individual is not up to it, the team is up to it. And as you saw just recently, we can use different forces to organize the activities and what the roles do in the project and when. And tomorrow, there will be much more on software development processes. We will look at some of the activities, the roles, and how to plan these. We will start looking at planning. Because these guys down here, they will fulfill the process roles, performing activities that uses and produces work products. And getting a hold of this, getting a grip on this system here, and define it and design it for our specific project. That's the key to success when developing software. So, that was it for today. Thank you very much, and see you Thursday. Okay.